ECG patterns and quickly identify abnormal segments. Abnormal segments can include variations in the QR. Normal segments will also be present. To tag an abnormal segment, click on it where it aligns with the cursor. However, be cautious not to click on normal segments, as this will result in a score deduction. Your score increases when you accurately tag an abnormal segment, but decreases when you mistakenly tag a normal segment. As you accumulate points, the speed of the scrolling waveforms will adjust, making the game progressively more challenging. Keep an eye on the score display to track your progress and aim for the highest score possible. Identify and click on abnormal ECG waveform segments as they scroll across the canvas. Avoid clicking on normal ECG waveform segments to prevent score deductions. Clicking on an abnormal segment earns you points, while clicking on a normal segment reduces points. The game speed increases as your score goes up, making it more challenging. Continuously monitor the score display to track your current score. The game ends when you decide to stop or when you reach a specified score goal. Aim to achieve the highest score and demonstrate your skill in recognizing abnormal ECG patterns. Welcome to the ECG Waveform Analysis Challenge. This interactive game offers a unique opportunity to test and enhance your skills in identifying abnormal electrocardiogram, ECG, patterns. In this challenge, you're not just playing alone, you're competing against our advanced robot algorithm designed to analyze ECG waveforms. As the waveforms scroll across your screen, your task is to identify and tag abnormal segments, such as irregular QRS complexes, missing P waves, or absent T waves. Be cautious, though, tagging normal segments will affect your score negatively. As the game progresses, the waveforms will move faster, increasing the difficulty. Keep track of your score and see how well you can do against our robot. But that's not all. This challenge also provides a unique learning opportunity. By comparing your scores with the robot's analysis, you gain insights into the complexities of ECG interpretation. The robot uses a sophisticated fuzzy logic algorithm to evaluate each waveform, offering a high-tech benchmark for your own assessments. Whether you're a medical professional, a student, or simply someone interested in biomedical engineering, this game is designed to test your skills and expand your understanding of ECG analysis. So, are you ready to take on the challenge and see how you stack up against our robot? Let the game begin. This interactive game is designed to test your skills in identifying abnormal ECG patterns. In this challenge, you will be competing against a robot algorithm. This robot, programmed in Python, analyzes ECG waveforms using fuzzy logic, but does not have prior knowledge of waveform labels. This means it operates solely based on the data it analyzes in real time, just like a human player. Your task is to observe the scrolling ECG waveforms, generated in JavaScript, and identify abnormal segments. The complexity lies in distinguishing between normal and abnormal patterns, such as variations in the QRS complex or the absence of specific waves. Clicking correctly on an abnormal segment increases your score, but incorrect clicks on normal segments will reduce it. The game's pace accelerates as you score more points, adding to the challenge. How the analysis works. The ECG waveforms you see on your screen are dynamically generated using JavaScript. This part of the code is responsible for creating both normal and abnormal ECG patterns, but it does not label them. Hence, when you and the robot algorithm analyze these waveforms, you're both starting from the same base of knowledge. The robot's decision-making process is handled by a Python-based fuzzy logic system. This system evaluates the waveforms based on several criteria, such as frequency, amplitude, and peak patterns, to determine whether a segment is normal or abnormal. However, it doesn't receive any direct information or labels about the waveforms. Its judgments are made solely based on its program analysis parameters. This setup ensures a fair comparison between your human analytical skills and the robot's program logic. It offers an engaging way to understand ECG interpretation and appreciate the application of fuzzy logic in biomedical analysis. Hey everyone tuning into the live stream, welcome. Today, we're diving into some exciting coding adventures, particularly focusing on our project involving ECG waveform analysis using fuzzy logic in a Python Flask app, and how noise impacts its performance. We've got four main files in play: index, HTML, waveforms, JS, game_logic, JS, and our Flask app.py. Let's make this more interactive and clear for all the enthusiasts out there. Our main goal is to enhance the user experience and understanding of how noise levels affect the fuzzy logic algorithm's performance in analyzing ECG waveforms. We're looking at a scenario where users can adjust the noise level and immediately see its impact on the algorithm's decision-making process. Here's a roadmap of what we can do. Noise level visualization. We can tweak game_logic, JS to visually represent the noise level on the ECG waveform. This could be done by altering the waveform's opacity or color intensity based on the noise level. Real-time feedback. Modify index, HTML and game_logic, JS to provide real-time feedback on the users and the algorithm's performance as the noise level changes. This could involve dynamically updating text or graphical elements to reflect current scores or decisions. Enhanced analysis display. In app.py, we can refine the analysis results returned to the client. Maybe include a breakdown of how each component of the fuzzy logic, like frequency, amplitude, etc., is influenced by the current noise level. Interactive noise control. Ensure the noise slider in index, HTML is effectively controlling the noise level in waveforms, JS. It should be responsive and reflect changes in real time in the waveform displayed. Debugging and optimization. Let's comb through the code to optimize performance, ensure there are no bugs, and everything is running smoothly and efficiently. Documentation and comments. Add comments and documentation in the code for clarity, especially around complex sections like the fuzzy logic implementation in app.py and the waveform generation in waveforms.js. User testing and feedback. We might want to think about how to gather user feedback on the interface and the overall experience. This could be a simple form or direct interaction during the live stream. Alright, let's roll up our sleeves and dive into the code. We'll start by focusing on enhancing the noise visualization and feedback mechanism. Keep your ideas coming in the chat. Let's make this session interactive and fun. Glowing Star Rocket PC. Alright, we've got our game screen showing the ECG signal with all the metrics and scores displayed. I see the fuzzy logic analysis results are live, including the raw frequency, positive and negative peaks, amplitude, and the final decision. So, if we're focusing on the noise aspect and its impact on the fuzzy logic's performance, here are some ideas. Visual feedback on noise. The noise slider is a great interactive tool. We can link the noise level visually to the ECG display. Maybe let the waveform's line thickness or jitteriness represent noise. Thicker, more jittery lines for high noise levels, and smoother, thinner lines for lower noise can make the impact of noise tangible. Performance metrics adjustment. The scores seem to be affected by the noise, as indicated by the fuzzy logic's decision-making. It might be helpful to display a live graph or a meter that shows the algorithm's confidence in its decision. As the noise increases, the confidence could decrease, reflecting the difficulty in analysis. Noise impact explanation. Let's include a brief on-screen explanation or a pop-up that describes why noise impacts ECG analysis. This could be a "Did you know?" section that gives snippets of info when the noise level changes, like higher noise levels can mimic ECG abnormalities, leading to false positives in detection. Dynamic scoring. Introduce a scoring multiplier based on noise level. The higher the noise, the more points a user gets for a correct hit, due to the increased difficulty. Display this multiplier on the screen to incentivize playing under harder conditions. Algorithm performance tracking. We could plot the fuzzy logic's performance over time against the noise level. This would be an excellent way to visualize how noise affects its accuracy. A simple line graph could work, plotting noise level on the x-axis and accuracy on the y-axis. In-game instructions update. Make sure the instructions clearly state how the noise affects gameplay. Players need to know what they're up against when they tweak the noise level. Highlighting the abnormal segments. When the decision is abnormal, we could briefly highlight the segment in a different color on the waveform. This immediate visual cue can help players understand what the algorithm is seeing. Remember, we're balancing education with engagement here, so let's make sure these changes keep the game fun and informative. If there's anything specific you'd like to see implemented first, or if you have any questions about the suggestions, let me know. Let's get coding.
Okay, you didn't pick up on the fact that the ECG in the example provided was normal. However, the fuzzy logic algorithm made the decision that the waveform is abnormal. The reason being that the abnormality score for normal waveform doesn't go low enough. Shall we adjust the rules some further? The membership functions seem correct. Yep.
Got it. The core issue here is that the fuzzy logic is tagging a normal ECG as abnormal. This suggests that our fuzzy logic rules or the scaling of input parameters might be too sensitive or not properly calibrated. Since the membership functions seem appropriate, we could look into adjusting the rule base to better differentiate between normal and abnormal ECGs. Let's consider the following. Refining the rules, we might need to redefine the rules to be more specific. For instance, if we're getting false positives on normal ECGs, it could mean that our criteria for likely, abnormal are too broad. Adjusting rule weights. If our fuzzy system allows it, we could assign weights to the rules, giving less weight to rules that are contributing to false positives. Fine-tuning input scaling. We should double-check the scaling of our inputs, the raw frequency, positive peaks, negative peaks, and amplitude. The fuzzy logic's decisions are highly dependent on how we scale these inputs. Threshold review. Look at the thresholds we're using for classifying the peaks and frequency. We may need to adjust the cutoff points where the system decides something is too many or too few. Analyzing overlapping functions. Ensure that the membership functions for our fuzzy sets don't have too much overlap, which can cause indecision or leaning too much towards one output. Introducing new antecedents. We might need more input parameters to improve decision-making. For example, we could consider the variability of the intervals between peaks or the presence of certain characteristic patterns. Defuzzification method. The method we're using to convert the fuzzy decision back into a single number, abnormality score, could also affect the outcome. We might need to switch to a different defuzzification method if the current one isn't giving us the granularity we need. Real data testing. To ensure our adjustments are effective, we'll need to test with a set of real ECG data, both normal and abnormal. This will give us a benchmark to compare against and validate our changes. Now, let's try tweaking these parameters. We might need a few iterations to get it just right, considering the complexity of ECG patterns and the inherent noise in the data. It's all about finding the sweet spot where our fuzzy logic is robust against noise, but still sensitive enough to catch real abnormalities.
Okay, there are a couple of issues here. Frequency doesn't actually do much in our case. The raw frequency is only changing from 3 to 5, depending on the number of peaks. Shall we replace this metric, this feature, by something else? Also, I think we're already doing it, but can we make sure we give priority to the number of positive and negative peaks as opposed to frequency and amplitude? Potentially, instead of getting rid of the frequency component, can we add a fourth feature? No, this would be a fifth feature. So we have positive peaks, negative peaks that should have higher priority. Then we have frequency and amplitude. Can we add 1 or 2 extra features and work from there?
Absolutely. If the frequency is not giving us significant insight, we can consider replacing it or diminishing its influence in the fuzzy logic decision process. Giving priority to the number of positive and negative peaks makes sense, as these are critical in identifying ECG abnormalities. Here are some steps and ideas for introducing new features and adjusting the prioritization. New feature, variability. We could add a feature that measures the variability in the intervals between consecutive peaks, both positive and negative. This can be a strong indicator of irregular heart rhythms. New feature, morphology. Another feature could be the morphology of the QRS complex, which could involve looking at the shape and duration. This would require a more complex analysis, but can provide a deeper insight into potential abnormalities. Deprioritizing frequency. If frequency isn't helpful, we can either remove it or reduce its impact in the rule set. This means adjusting the rules so that the decision relies more on peaks and the new features. Adjusting membership functions for peaks. Since we want to give more priority to peaks, we can adjust their membership functions to have a wider range, ensuring that changes in their number significantly influence the outcome. Tweaking rules. Modify the fuzzy rules to reflect the new prioritization. For example, If positive peaks are too many or too few, and negative peaks are too many or too few, then abnormality is likely. If the variability is high, then abnormality is likely, regardless of the amplitude. Composite feature. Consider creating a composite feature that combines several of these metrics into one. For example, a complexity feature that considers peaks, variability, and morphology together. Input feature scaling. Ensure that the scaling of these new features is in line with the expected range of values in a normal ECG. We don't want the scaling to be too sensitive or too broad. Incremental testing. With each new feature or adjustment, test the system incrementally to observe the impact. This will help fine-tune the system without overcomplicating it. Rule refinement. Continuously refine the rules as we introduce new features to ensure they're all working in harmony and providing meaningful input to the decision-making process. For the fourth feature, if we go with variability, it could be calculated as the standard deviation of the time intervals between consecutive peaks. This would give us a direct measure of the rhythm's regularity. Implementing these changes will likely require a fair bit of coding and testing. We'll need to update our data processing functions to calculate the new features, modify the fuzzy logic rules, and potentially adjust the user interface to display the new information. Would you like to start with one of these features, or do you have a different one in mind? Let's iterate on this and see how our fuzzy logic system improves.
Okay, let's go over these things one by one. Regards the new feature, so it's suggesting variability and morphology. Well, we'll need to know exactly how they work and add to the decision process. So with variability, talking variability of the intervals between consecutive peaks. And that sounds good, but we don't want to do any magic numbers. Is there some sort of golden ratio between P, Q, R, S, T waves? Yeah, I think this one will be problematic to get right. Unless we do an R peak detector and then look at the timing before and after. Regards morphology. So looking at the shape and the duration. Yeah, need more details on that. How do you suggest doing it exactly? Just to be clear, in the current setup, we have a single ECG complex, a PQRST waveform coming through the screen at a time. So this is not a good assumption, because in reality the ECG waveform will be continuous. So based on this, a morphology analysis might not work. Yes, I would like to try and deprioritizing frequency. Doesn't seem to do much, considering its low numbers for the different waveforms. So yes, we would like to keep it, but make sure it doesn't have much weight on the output. Now adjusting the membership functions for peaks. Yeah, I think we already have something that makes sense. Can you double check the code? I don't want to be tweaking this too much. might need more details on the composite feature. So it's saying combining some of the features together. Aren't the fuzzy logic rules already doing this? I'm pretty sure they are. We are doing scaling normalization already. So for the frequency and amplitude, the numbers are turned into between 0 and 1. Obviously, positive peaks and negative peaks are just used as raw numbers. Yes, we might. This is probably the most important bit, is keep refining the rules. Also, do you have any suggestions as to how to make the rule adjustment and the membership function thresholds adjustment to be available on the front panel? Yep.
Certainly, let's break this down step by step and ensure we're clear on the path forward. Variability. We can define this as the standard deviation of the intervals between consecutive peaks. To avoid magic numbers or arbitrary thresholds, we can establish baseline variability from typical ECG data and express deviations from this baseline as a ratio or a percentage. This would be a relative measure rather than an absolute one, avoiding the need for magic numbers. Morphology. Given the setup where only one ECG complex is displayed at a time, a full morphology analysis might indeed be impractical. However, we can still analyze the morphology of each wave within the single displayed complex. For example, we could measure the relative sizes or areas under the P, Q, R, S, and T waves within a single complex. This would be a simplified morphology analysis. Deprioritizing frequency. Since frequency isn't providing much insight, we can adjust its influence in the decision-making process by weakening its associated rules within the fuzzy logic system. For example, we could set the rule that only extreme frequencies contribute to the abnormality decision. Membership functions for peaks. If the current membership functions for peaks make sense, we can leave them as is. However, if we're introducing variability as a new feature, we should ensure that the peak membership functions still align well with this addition. Composite feature. In fuzzy logic, the rules inherently combine multiple features to make a decision. A composite feature would be a pre-fuzzification step, where we mathematically combine certain features before feeding them into the fuzzy system. For instance, we could create a complexity index by combining the number of peaks and their variability. However, given that our fuzzy logic system already does this to some extent, adding a composite feature might be redundant unless it provides a new perspective or simplifies the system. Rule refinement. Continuous rule refinement is key. We can introduce a feedback loop where we adjust rules based on the performance of the system with real data. For instance, if the system frequently misclassifies a normal ECG with a certain peak profile as abnormal, we would adjust the rules to correct this. Front panel adjustments. Making rule adjustments and threshold settings available on the front panel is a great idea for users who want to dive deeper or have advanced knowledge of ECGs. This would involve creating a user interface that allows for dynamic changes to the fuzzy logic system and immediately reflects those changes in the analysis. Here's a technical approach to implementing some of these adjustments. For variability, we'd add a function to calculate the time intervals between peaks, then compute the standard deviation of these intervals. For morphology, as it might be too complex for our current setup, we could leave it out for now or focus on the R wave since it's the most prominent feature in an ECG. For rule adjustment on the UI, we could implement sliders or input fields that allow users to adjust the weight of each feature in the fuzzy logic rules, which would be a more advanced feature. Before proceeding with these changes, we should confirm which adjustments or additions will bring the most value to the system given the current limitations and what the users of the system are most interested in exploring. Understood. Let's get more specific with the code and how we can incorporate variability into the fuzzy logic for ECG analysis. For the variability feature, we could calculate the standard deviation of the RR intervals, the intervals between consecutive R peaks, which are typically the most prominent points on an ECG. Here's a high-level outline of how this could be implemented in the process_data function in the app.py file. Calculate RR intervals. Detect. Detect R peaks within the waveform. Calculate the intervals between consecutive R peaks. Determine the standard deviation of these intervals. Define a new antecedent in the fuzzy logic system for variability. Create membership functions for variability, e.g., stable, moderate, high. Add new rules that incorporate this variability metric. Add new controls to adjust the thresholds for the variability membership functions. Display the variability score on the front panel. Here's some pseudocode for these steps. This is a simplified example and assumes you have a function detect_R_peaks that can accurately find R peaks in the waveform data. You'd also need to define the time underscore between underscore samples based on the sample rate of your ECG data. Once you've updated the fuzzy logic system, you'll need to add the variability into the fuzzy control system and update the rules accordingly. Then, to enable real-time updates from the front panel, you need to set up a system where changes to the controls send requests to the Flask backend, which then updates the fuzzy logic system and sends back the updated analysis. This approach allows a medical data researcher to understand and interpret the results because it uses well-established ECG analysis metrics, like RR intervals, avoids arbitrary thresholds by normalizing against typical values, and provides a way to adjust the system in real time based on expert feedback. Remember, you'll need to test these changes extensively with both normal and abnormal ECG data to ensure the system behaves as expected. Given the constraint of having single PQRST waveforms, rather than consecutive ECG cycles, we can't measure RR variability. Instead, we'll have to focus on features we can extract from individual waveforms. Here's an adjusted approach to ensure normal ECG waveforms yield a lower abnormality score. Adjust membership functions. We can tighten the normal range for our existing antecedents. This means making the normal membership functions for the number of peaks and amplitude more stringent. Refine rules. Adjust the rules to ensure that when all features fall within the normal ranges, the abnormality score is low. Additionally, introduce rules that heavily penalize scores when features fall into normal membership functions. Defuzzification strategy. The method used to defuzzify the fuzzy results to a single abnormality score can significantly impact the results. We can adjust this method to bias towards lower scores for normal readings. New antecedent for shape analysis. We could introduce an antecedent that represents the sharpness of the R wave, which could be determined by the width at half the peak's height, a common measure in signal analysis. A normal R wave has a specific sharpness range, while abnormal waves can be either too sharp, spiky, or too blunt, rounded. Antecedent for baseline wander. Introduce a measure for baseline wander, which is the variation in the baseline of the ECG. A normal ECG should have minimal baseline wander. Here's how you might implement some of these suggestions. By tightening the normal membership functions and adding a new antecedent for R wave sharpness, we can make the system more sensitive to variations in the waveforms that are characteristic of abnormalities. Additionally, by refining the rules and the defuzzification method, we can better ensure that normal ECGs result in low abnormality scores. As always, after implementing these changes, we want to test with a variety of ECG waveforms to fine-tune the membership functions, rules, and normalization methods to ensure they're accurately reflecting the medical data researcher's expertise. Certainly, let's clarify the use of global minima and maxima for the peaks within the code. The purpose of having these global values is usually to normalize the feature values so they fit within a specific range, like 0 to 1, which is a common requirement for many machine learning algorithms, including fuzzy logic systems. In the provided pseudocode, it seems that there's a generic mention of global min and max values for peaks without specifying whether they're positive or negative. This is indeed a bit unusual since we typically need to track the minima and maxima for positive and negative peaks separately due to their distinct roles in ECG analysis. Let's assume we should have separate tracking for positive and negative peaks. The code would need to differentiate between these two types of peaks and maintain separate global values for them. Here's how you could update the code. The update_global_ranges function might look something like this. In this setup, whenever you process a new waveform, you call update_global_ranges for both positive and negative peaks to keep these global values up to date. Regarding the usage of these global min, max values, they would typically come into play when you're normalizing the peak counts before feeding them into the fuzzy logic system. If you're not seeing this normalization step in the code, then there might be an oversight, or the normalization may not be necessary for the current implementation. However, if the code is meant to use these global values for normalization and isn't doing so, you need to add that step before the fuzzy logic analysis. This would involve adjusting the peak count values based on the global min, max values to ensure they fit within the expected input range of the fuzzy system.
Yeah, I haven't changed anything and it started to work. This is always nice, isn't it? Well, I just cleaned up the code a bit. Haven't made any major changes, I would think. Just started to work again. So for a normal ECGs, we now get 0.269. Okay. Now it's labeling everything as normal. Why? And the only thing that changes is the global minimum maximum. Okay, that's a good response. Yeah, those thresholds should be getting better over time. I think this is what happened here. Yeah, I get a 0.25. Yeah, we really shouldn't be getting that. That would be a miss. And another miss. This rules the fuzzy logic analysis thing. Should just make sense. Can we quickly go over this entire function step by step and make sure that all the membership functions just make sense? And then we'll have to go over each rule one by one, and again make sure they make sense and are correct. Ideally we will have a neurologist or cardiologist looking at the this signal, but unfortunately we don't have money to pay one. So can you act as an ECG waveform signal specialist and make sure the fuzz logic algorithm make sense by again going over each membership function and all the rules. Yep.
Sure, let's walk through the fuzzy_logic_analysis function and evaluate the membership functions and rules, with the aim of making the logic as sensible as possible from a cardiological perspective. Frequency, backquote. Low, 0.5. This seems to represent a very low frequency, which could be indicative of bradycardia if considering heart rate. However, since we're looking at single waveforms rather than heart rate, a low frequency might not be relevant.
No, it is correct. It is not relevant. I don't think we ever get that frequency. The problem with frequency is that we're only getting numbers 3 and 5, which kind of makes sense because we, looking at the individual waveforms. So it's not actually changing much. We just essentially know that the normalized frequency between 0.5 to 0.7 is okay. It's normal. Well, because it's 3 or scaled 0.6 for pretty much all the waveforms, and 5 for this one where the peaks are closer together. So this might be relevant later when we add more different types of ECG waveforms. Yes, we'll try to have more variability there. So it might become relevant later.
Normal, 0.5, 0.6, 0.7. It's unclear what frequency refers to since we're analyzing single waveforms. Typically, frequency would not apply here and might be a carryover from an earlier version of the system that dealt with sequential waveforms.
Well, yeah, that's a fair point. Yes, and this is why we're giving frequency a low priority as well.
High, 0.711, similar to low. This would be more applicable if analyzing a series of waveforms.
No, so we don't do a series of waveforms. And in this particular case, we might have another tool that does that. Now, amplitude. Normalized amplitude, say for this waveform is 0.6, 0.9 for a normal ECG.
Which could indicate issues like low electrical activity within the heart or distant electrode placement. This could be a useful measure. Represents high amplitude, which could indicate ventricular hypertrophy or other conditions leading to increased electrical activity.
Okay, so for amplitude, I mean, it could be also noise, couldn't it? So we first have to assume we're actually looking at the PQRST complex before making any assumptions. So it has to be like a multi-stage analysis. So ideally, we probably should be detecting if there is a complex or not. It could be probably a good first stage analysis.
Too few, 0, 1, 2.5. Since we're looking at single complexes, too few doesn't make sense unless you're counting the number of positive deflections in a complex. Normally, you would expect one positive peak, the R wave, in a standard ECG complex.
Well, why shouldn't be 3? It was a network error. Well, my network is okay. Let's try to regenerate.
Absolutely. I can guide you through the fuzzy logic function and evaluate the membership functions and rules with a focus on ECG waveform analysis. Let's start with the membership functions.
Okay, so we already covered the frequency. Let's do positive peaks.
Positive peaks. Too few, 0, 1, 2.5. This suggests that up to 2.5 peaks are considered too few, which seems reasonable if we expect around 3 peaks for a normal ECG. Normal, 2.5, 3, 3.5. Again, a narrow range centered around the expected 3 peaks for a normal ECG. Too many, 3.5, 4, 5. This captures anything above 3.5 as too many.
Okay, so those numbers sound legit. Well, to me. Didn't I tell it to act like a cardiologist?
Too few, 0, 0, 1. This indicates that 1 or fewer peaks are too few. Normal, 0.5, 1.5, 2.5. This is broader and allows for some variability in what's considered normal. Too many, 2, 3, 4, suggesting that above 2 starts to be too many.
Yeah, it's not making any. Yeah, this is the general stuff. Yes, amplitude 0.5. Yeah, that's what we set it to, but it's not giving any ideas as to if it's normal or not. get like the abnormality score. So we have unlikely, possible, and likely.
Unlikely, 0, 0, 0.36. This is a reasonable range for unlikely abnormality, capturing scores close to 0. Possible, 0.35, 0.4, 0.45. A very tight window for possible abnormality, not giving much room for uncertainty. Likely, 0.44, 1, 1. This implies that scores above 0.44 are likely abnormal.
Right, shall we just split it three-way? Let's see if GitHub Copilot can quickly do this. But understand what I mean. Got to be GPT-4. Didn't actually do anything. Let's open the chat. Okay, let's split 3 equal ways. It's getting that code alone. It's the scale of the what's the universe range? Shouldn't be just between 0 and 1. Okay, considering GPT-4 has all the context, just ask it to do that.
To split the abnormality membership functions into 3 equal ranges, we should adjust the triangular membership functions, TRIMF, so that they cover the universe of discourse, which in this case is from 0 to 1, evenly. Here's how you could do it. The unlikely category covers scores from 0 to 0.33. The possible category starts where unlikely left off, peaking at 0.5, and ends at 0.66. The likely category picks up from 0.66 to 1. This division ensures that each category covers an equal third of the range of possible scores, preventing any overlap between unlikely and likely. This way, the system has a balanced and clear-cut approach to categorizing the abnormality scores, with a neutral zone, possible, that provides a transition between the two extremes. When implementing this, it's important to remember that the fuzzy logic rules will interact with these membership functions. The rules should be revisited to ensure they're still appropriate for the new membership function definitions. For instance, rules that were designed with the previous overlap in mind may now behave differently and might need to be adjusted accordingly.
There is some more general problem with the code. I think it's to do with how the thresholds, the global minima maxima, are being calculated and how they diverge. Can we check that in the code? and find the bits that might affect this. Like, the question is how repeatable is the abnormality score between different runs, specifically considering that the global variables are set to not available. Yep.
In the provided code snippets, there's a mention of global variables for tracking the minimum and maximum values of certain features, such as the number of peaks. However, if these global variables are initialized to none, or are not initialized at all and hence default to Python's none, there could be issues when the code tries to use them for the first time. If these variables are meant to track the minima and maxima across multiple runs of the application, i.e., they're not reset between runs, then it's crucial that they are initialized properly and updated in a consistent manner. Let's consider two scenarios. Persistent across runs. If the global min, max should persist across multiple runs, they should be stored externally, e.g., in a file or database, and loaded into the application when it starts. Reset each run. If they should reset each time the application runs, they need to be initialized to appropriate values within the application's startup logic. The repeatability of the abnormality score between different runs will depend on these global variables being handled correctly. If the global min, max are not initialized or updated correctly, the normalization of the input features to the fuzzy system could be inconsistent, leading to different abnormality scores for the same input data on different runs. Here's how you might ensure consistent initialization and updating of these global variables in your Flask application. This code ensures that the global min and max values are initialized to values that will be updated with the first set of real data. The update function update_global_min_max will adjust the global min, max appropriately with each new value. Remember, these global min, max values should be used to normalize the input features before passing them into the fuzzy logic system, which will make the abnormality score more repeatable between runs. If you're experiencing divergence in the global min, max values, it may indicate that the application is not consistently updating these values between runs. You should also ensure that the update logic is correctly applied after every new data input, not just at the application startup. To enhance the repeatability of the abnormality score every time you run the web application, we need to ensure that the factors influencing this score are consistent across runs. Let's address the key areas where variability can occur. Initialization of global variables. Currently, you have global variables for tracking minimum and maximum values of frequency and amplitude. These are initialized as none, which means they're set during the first execution of process_data. However, their values will differ between runs unless they are reset or initialized consistently. If these variables are meant to accumulate knowledge across runs, consider persisting them in a file or database and loading them when the app starts. If they're meant to be session-specific, they should be reinitialized each time the app is started. Normalization method. The normalize function is used to scale the amplitude, but it relies on global min and max values, which can vary. Ensure that these values are set in a consistent manner. If they're based on the incoming data, the scaled results may vary across runs due to different datasets. To avoid this, consider using fixed min and max values based on typical ECG data ranges. Handling edge cases in normalization. The normalize function returns 0 if max_val equals min_val. This is an edge case, like a flatline ECG, and might need special handling. Decide how you want to treat such cases to ensure they don't skew your results unexpectedly. Fuzzy logic system consistency. The construction of your fuzzy logic system, abnormality_analysis, is dependent on the input data. Ensure that the membership functions and rules in the fuzzy logic system are well defined and not influenced by varying data. The way these are set up right now seems to be static, which is good for repeatability. Testing with consistent datasets. To check the repeatability, use the same set of test data across different runs. This will help you determine if the scores are consistent for the same input. Logging and debugging. Since you're running a Flask app, consider adding logging statements in key areas of your code, especially where global variables are updated, and in the process_data and fuzzy_logic_analysis functions. This can help you track down inconsistencies. Resetting state for each run. If you want the app to behave the same way each time it started, regardless of previous runs, ensure that any state, like global variables or files storing state, is reset or reinitialized when the app starts. By addressing these areas, you should be able to make the abnormality score more repeatable and reliable across different runs of your application. To improve the repeatability of the abnormality score between different runs of your application, we need to ensure consistent normalization and handling of the global variables. Here are specific code change suggestions. Persisting global variables. Save the global variables to a file or database at the end of each run and load them when the application starts. This way, the values for global_min_amp, global_max_amp, etc., remain consistent across runs. Fixed normalization ranges. Instead of using dynamic global min, max values for normalization, use fixed ranges based on standard ECG data characteristics. This ensures that the scaling is consistent regardless of the data in a specific run. Edge case handling in normalize function. Modify the normalize function to handle edge cases more appropriately, rather than defaulting to 0, which might skew your results. Here's how you can implement these suggestions. In this implementation, the global variables are saved or unloaded from a file, ensuring consistency across runs. The normalize function now uses a fixed range for normalization, ensuring that the scaling is the same every time. Remember, the fixed ranges in the normalize function should be set based on the typical range of values you expect for your application's data. You might need to adjust these ranges based on the characteristics of your ECG data. This approach should make the abnormality score more consistent across different runs of the application. Understood. Let's focus on simplifying and streamlining the application for user feedback. Setting the global variables to reasonable default values is a practical approach. Also, replacing the frequency feature with a QRS shape analysis is a good idea, given that QRS morphology is a significant indicator in ECG analysis. Set reasonable defaults for global variables. Define default values that reflect a typical range for the ECG data you're analyzing. This will ensure consistency across runs without needing external storage. Replace frequency with QRS shape feature. Assume the presence of an R peak and assess its sharpness. Sharpness can be quantified by measuring the width of the R peak at half its maximum amplitude, a common approach in waveform analysis. Here's how you might implement these changes. This implementation introduces a measure for the sharpness of the R peak, adding it to your fuzzy logic analysis. The calculate_R_peak_sharpness function quantifies the sharpness, which is then used in the fuzzy logic system to assess the waveform's normality or abnormality. Remember, the values for the global variables and the exact definitions of the membership functions should be adjusted based on your specific ECG data and requirements. This setup should give you a more focused analysis for user feedback, centered around key ECG features. Understood. Let's focus on simplifying and streamlining the application for user feedback. Setting the global variables to reasonable default values is a practical approach. Also, replacing the frequency feature with a QRS shape analysis is a good idea, given that QRS morphology is a significant indicator in ECG analysis. Set reasonable defaults for global variables. Define default values that reflect a typical range for the ECG data you're analyzing. This will ensure consistency across runs without needing external storage. Replace frequency with QI as shape feature. Assume the presence of an R peak and assess its sharpness. Sharpness can be quantified by measuring the width of the R peak at half its maximum amplitude, a common approach in waveform analysis. Here's how you might implement these changes.
Okay, we're just getting rid of frequency as a feature and adding R peak sharpness, which will have a normal or abnormal membership function. So we're calculating membership based on the calculate membership function as an input of data amplitude, positive peaks, negative peaks, and R peak sharpness. In theory, frequency should be commented out everywhere. Okay, now the Python code is working again, but obviously JavaScript will be complaining. Can we update this based on the recent Python script changes? No, that's wrong. Yeah, it doesn't have the whole context. Don't want to display frequency anymore. So we have positive peaks, negative peaks, raw amplitude. No, it's not abnormality score. I think we also removed the normalized amplitude. Yeah, we removed normalized amplitude as well. It's not pulling a code from another file, which is a bit problematic. Yeah, I could return the normal abnormal as well for this one. Okay, we really need the GitHub copy won't do it for us. We really need something heavier. So we have a Python code. The game logic. We don't worry about waveform.js, shouldn't require any changes. Okay, so made some necessary changes in the Python code provided above. and we are trying to modify the JavaScript to match the changes in Python. Essentially what we did is remove the frequency metric, so the frequency feature is not required anymore, and we added an R peak sharpness feature. Can you check the code? Yep.
Sure, let's go through the modifications required in both the Python and JavaScript code to reflect the removal of the frequency feature and the addition of the R peak sharpness feature. Remove frequency feature, Comment out or remove any code related to the frequency feature, including its global variables, calculation, and its use in the fuzzy logic system. Add R peak sharpness feature, ensure that the calculate_R_peak_sharpness function is correctly implemented and used in the process_data function. Add the R peak sharpness as an input to the fuzzy logic system in the fuzzy_logic_analysis function. Remove frequency display, comment out. Display R peak sharpness. Add elements to display the R peak sharpness value returned from the server. Let's revise the provided Python code accordingly. In your game_logic.js, update the display analysis result function to reflect the changes. Ensure you also have the corresponding HTML element with id equals R peak sharpness to display this value. These changes will align the Python backend and the JavaScript frontend with the new feature set, removing frequency and adding R peak sharpness. Remember to test thoroughly to ensure that the integration between the front-end and back-end works as expected and that the fuzzy logic system behaves correctly with the new inputs. To evaluate the R-peak sharpness calculation and its membership function and rules, let's review what we know and what we expect. R-peak sharpness calculation. The sharpness of the R-peak is being assessed by the inverse of the width at half the maximum amplitude of the R-peak. A sharp R-peak would typically have a small width at half its maximum, leading to a higher sharpness score. Conversely, a blunted R-peak would have a larger width and hence a lower sharpness score. Membership function. The membership function for R-peak sharpness has been defined as follows. Normal, fuzz, trimph, R_peak_sharpness, universe, 0.3, 0.5, 0.7. Abnormal, fuzz, trap MF, R_peak_sharpness, universe, 0, 0.2, 0.8, 1. Rules. There is one rule concerning the sharpness score. Control. Rule, R_peak_sharpness, abnormal, abnormality, likely. Given the uploaded examples. The first example has an R-peak sharpness of approximately 0.043, which is significantly less than 0.3. This should strongly trigger the abnormal membership function, increasing the abnormality score. The second example has an R-peak sharpness of 0.5, which falls perfectly in the normal range of the membership function. This should not contribute to an increased abnormality score. Both examples seem to be consistent with the set rules and membership functions. If the sharpness score is close to 0, indicating a very blunt R wave, it's marked as abnormal, which should be the case with the first example. If the sharpness score is at 0.5, a typical sharp R wave, is marked as normal, which aligns with the second example. From the provided information, it seems the calculation and the fuzzy logic system are working as intended. However, you would still need to validate the system with a wider range of known ECG data to ensure it correctly identifies abnormal R-peak sharpness and correlates well with genuine ECG abnormalities.
Well, in this case, it's actually not working correctly. I actually expect the opposite. The lower peak sharpness is actually for a normal QRS complex, whereas the 0.5 value is for a peak that does not look normal.
If the lower R-peak sharpness value indicates a normal QRS complex, and the value around 0.5 is abnormal, then the membership functions and the associated rule need to be revised to reflect this understanding. Let's redefine the membership functions for R-peak sharpness to align with your expectations. Normal R-peak sharpness, sharp R-peaks, which indicate a normal QRS complex, will have a low width at half maximum, thus a higher sharpness score. We need to adjust the membership functions so that higher sharpness scores fall into the normal category. Abnormal R-peak sharpness, blunted R-peaks, which indicate an abnormal QRS complex, will have a higher width at half maximum, thus a lower sharpness score. We need to ensure that these scores are categorized as abnormal. Here's how the membership functions and rules can be adjusted. With these changes, an R-peak sharpness near 1, which indicates a sharp R-peak, will fall under normal. An R-peak sharpness of 0.5, which indicates a not sharp R-peak, will fall under abnormal. You should now retest your application with this new configuration to see if the abnormality score behaves as expected. It's crucial to thoroughly validate the system with a set of ECGs that have been labeled by a clinician to ensure the fuzzy logic accurately reflects clinical interpretations.
Okay, for the R peak sharpness, we want to have the 3 level, low, normal, and high. A second point is that we want to fix the calculation. We want to figure out why a normal ECG producing such a low peak sharpness value. Yep.
To address the issue with R peak sharpness, we need to adjust the membership functions. We will define 3 levels for R peak sharpness as low, normal, and high. The normal category should encompass the expected sharpness of a typical R peak, while low and high will capture the sharpness values that stray from the norm. Review the calculation method. We need to ensure that the calculation of R peak sharpness is correctly identifying the R peak and measuring its width at half maximum. A normal ECG producing a low sharpness value might indicate that the peak detection or width calculation isn't being done accurately. Here's how we can adjust the membership functions. To troubleshoot the calculation, let's go through the calculate_R_peak_sharpness function. Ensure R peak detection. Verify that the R peak is being correctly identified as the highest peak in the waveform. Correct width measurement. The width should be measured at half the R peak's amplitude. Ensure the correct indices are being found where the waveform crosses the half maximum threshold. Review normalization. If there is any normalization being applied to the sharpness score, it should be reviewed to ensure it's appropriate. Let's refine the calculation in the calculate_R_peak_sharpness function to make sure it correctly captures the expected behavior. This updated function should be more robust in calculating the R peak sharpness. It now handles cases where the waveform might not cross the half max value and normalizes the sharpness score by the width at half maximum. If the sharpness score is still not as expected, you may need to further investigate the waveform data and ensure that the preprocessing, e.g., noise filtering, Ensure R peak detection. Verify that the R peak is being correctly identified as the highest peak in the waveform. Correct width measurement. The width should be measured at half the R peak's amplitude. Ensure the correct indices are being found where the waveform crosses the half maximum threshold. Review normalization. If there is any normalization being applied to the sharpness score, it should be reviewed to ensure it's appropriate. This updated function should be more robust in calculating the R peak sharpness. It now handles cases where the waveform might not cross the half max value and normalizes the sharpness score by the width at half maximum. If the sharpness score is still not as expected, you may need to further investigate the waveform data and ensure that the preprocessing, e.g., noise filtering, is adequate. Based on the provided examples and the calculate_R_peak_sharpness function, the low sharpness score for what appears to be a normal ECG waveform suggests that the sharpness calculation may not be effectively capturing the characteristic of the R peak. Let's consider possible issues and their solutions. Noise in the waveform. If there is noise in the waveform, it can affect the detection of the actual peak and the calculation of its sharpness. Make sure the waveform is properly filtered before the sharpness calculation. R peak identification. The assumption that the R peak is the maximum point in the waveform may not hold if there is noise or other artifacts. More sophisticated peak detection might be required. Half maximum calculation. The method of calculating the width at half max might not be robust to noise or multiple crossings of the half max value. Inverse of width. Using the inverse of width may not be the best measure of sharpness. A more robust measure could be more suitable. Given these points, here are some code changes to address these issues. In this revised function, we apply a median filter to reduce noise. You might need to tweak the filter type and parameters based on the characteristics of your ECG data. We search for the last index before the R peak and the first index after where the waveform crosses below half max. This approach is more robust to noise. We've changed the sharpness score to be the actual width at half max, rather than its inverse. You may decide to keep the inverse if that better suits your definition of sharpness. If so, make sure to handle the division by zero case. ECG waveform preprocessing. Ensure the ECG waveform is preprocessed correctly before the sharpness analysis. This includes noise reduction and potentially R-wave enhancement. Peak detection algorithm. If necessary, implement a more sophisticated peak detection algorithm that can handle noise and more complex waveforms. Clinical validation. The interpretation of sharpness and other ECG features should be validated with clinical experts to ensure they accurately reflect the physiological characteristics of interest. After implementing these changes, rerun the analysis with various ECG waveforms to validate the changes. The error message you're encountering suggests that the fuzzy logic system's rules are not being activated by the input values provided. This can happen if the inputs do not fall within the expected range of the membership functions or if there's a logical inconsistency within the rules that doesn't allow any of them to fire. Here are some steps to troubleshoot and resolve this issue. Review membership functions. Ensure that the membership functions for each input cover the entire range of possible input values. There should be no gaps where an input value could fail to activate at least one membership function. Check rule connections. Make sure that the rules are structured in such a way that it's possible for each antecedent to trigger at least one consequent. If there's a logical gap where certain combinations of antecedents cannot lead to any consequent, you'll get this error. Validate inputs. Before calling the compute method on the fuzzy control system, check that the inputs are within the range you've defined in your antecedents. For example, if your antecedent for the R peak sharpness is defined over the range 0, 1, but the calculation returns a value greater than 1, the system will not be able to find a corresponding rule. Default values. Consider defining default rules that catch any inputs that do not fit within the main rules. For instance, if none of the specific conditions are met, you can have a default rule that sets the output to a neutral or middle value. Here's a quick check you can add to your code right before you run the compute method to ensure that the inputs are within the expected range. This check will give you a clear indication if your inputs are within the range and will activate the rules as expected. If they do not, you'll need to adjust either the inputs or the rules to ensure proper activation. This check will give you a clear indication if your inputs are within the range and will activate the rules as expected. If they do not, you'll need to adjust either the inputs or the rules to ensure proper activation. The error message you're encountering, generator, object has no attribute, items, suggests that there's an attempt to access the items method on a generator object, which is not valid since items is a method associated with dictionaries, not generators. This could be occurring in the section of the code where you're iterating over the antecedents of the control system to check if the inputs activate the rules. It looks like the antecedents is expected to be a dictionary, but it's actually a generator. Let's fix this issue. Here's how you can modify the code. In the analyze_waveform function, you're attempting to iterate over the antecedents of the control system, which should be a dictionary-like object. However, it seems that it's being treated as a generator instead. Make sure that abnormality_analysis, control, antecedents returns a dictionary-like object that allows iterating over its items. For the calculate_R_peak_sharpness function, you're now applying a median filter to the waveform data to smooth out the noise, which should help in identifying the R peaks more accurately. After locating the left and right crossing points, you're calculating the width at half maximum, which gives you the sharpness score. It's essential to note that a lower width at half maximum would indicate a sharper peak. In the fuzzy logic analysis, you're using the raw amplitude and sharpness score directly. If you normalize these values, ensure that the normalization process is consistent and correctly scales the values to be within the expected range for the membership functions. To resolve the error message, ensure that you're iterating over a dictionary. If abnormality underscore analysis, control, antecedents is a generator, convert it to list or dictionary first before iterating. Here's how you could modify the relevant section. Ensure to replace the placeholder data, var underscore name, with the actual values from the processed data that need to be fed into the fuzzy control system. If data does not contain the right keys or values, you will need to align it with the expected input format for the fuzzy control system. Absolutely, you can perform a check for all the input variables in the control system. This would ensure that every input activates at least one of the corresponding fuzzy sets in their respective antecedent objects. If any of the inputs do not activate a term, you may need to revise your membership function definitions or the range of input values to ensure that your system can handle all expected input scenarios. Here's a sample code snippet to perform this check. This snippet loops through each antecedent, input variable, in the control system and computes the degree to which each term is activated by the given input value. If no terms are activated for a particular input, it prints a warning message. You can then decide how you want to handle such cases before proceeding to compute the output of the fuzzy system. Certainly, I can guide you through a refactored version of the analyze_waveform function that includes the check for all the variables in the control system. The revised function will ensure that each input variable activates at least one membership function before proceeding with the computation of the fuzzy logic system. Convert_processed_data is assumed to be a function that takes the raw processed data and converts it into the format expected by the fuzzy control system. Construct_response_data is assumed to be a function that takes the simulation object after compute has been called and the converted processed data to create the response data object. Check_rule_activation is a function that checks if the inputs activate the rules before the computation of the control system output. The try except block is used to handle any exceptions that may occur during processing and provide an appropriate error response. You would need to implement the missing helper functions, convert_processed_data and construct_response_data, based on the specific details of your application. The check_rule_activation function is provided in the snippet above. Sure, let's recap the rollercoaster ride we've had with this ECG analysis app and wrap it up with a light touch. Recap of the Odyssey. We started with a grand plan to interpret ECG waveforms using fuzzy logic. Our noble quest was to distinguish the normal from the abnormal, without calling upon a cardiologist. The plot thickened as we tossed in some features, peaks, amplitudes, and a daring hero named R peak sharpness. Our fuzzy logic rules were like a tightrope walker, trying to balance sensitivity and specificity without falling into the pit of false alarms or misses. Along the way, we faced the hydra of code issues, changing membership functions, sneaky global variables, and the notorious generator has no attribute items beast. We talked about scaling the sharpness for better insights, but our sharpness score turned out to be as blunt as a butter knife in some cases. Through trials and tribulations, our application morphed and evolved, shedding its frequency feature like a snakeskin, and embracing R peak sharpness as its new shining armor. As it stands, it's like a compass that sometimes points north and other times leads you to Narnia. It has potential but needs refining to ensure it consistently points in the right direction. Its usefulness hangs in the balance. It could be a treasure trove for teaching, a nifty tool for nerds, or a curious contraption for the clinically inclined. There are several established ECG analysis tools out there with names that sound like space stations, like GE's Muse or Philips' Trace Master View, equipped with armies of algorithms and battalions of beats to analyze. Some are like wise old wizards, packed with decades of research and clinical trials, while others are more like apprentice sorcerers, still learning the spells of specificity and the incantations of sensitivity. If our ECG game were a patient, it would be in the needs observation ward rather than running marathons. But hey, with a bit more TLC, who knows? It might just get there. So, here's to our fuzzy logic quest, where the only thing sharper than our R peaks is our wit, and the only thing irregular than the heartbeats are the bugs in our code. In all seriousness, the concept is solid, and with some debugging, fine-tuning, and a dash of humor to keep spirits high, this app can indeed become a handy tool for ECG enthusiasts and professionals alike. Keep the defibrillator close, though, you never know when you'll need to jumpstart the system back to life.